Hello, everyone. Thank you for attending this session. This talk titled The Red Square, Mapping the Connections Inside Russia's APT Ecosystem. Let me give you a short introduction about this talk. In the last 15 years, many Russian operations and malware families were publicly exposed by different security vendors and intelligence organizations. Those publications focus on specific Russian actors or operations, but the bigger picture remains unclear, which is the Russian APT ecosystem as a whole. And we wanted to get a better understanding of how this ecosystem looks like in terms of the connections between the different components, and that is why we conducted this research. We're really happy to be here today and to show the results. And we will also present several open source tools that we built during our research and now can be used by you guys, the community, for further investigation. But before we start, I would like to introduce ourselves. So my name is Eitan, and I'm the VP of Research at Intezer.
Hello, I'm Itay Cohen. I'm a reverse engineer in Checkpoint Research. I'm also one of the developers of Radar2, the open source reverse engineering platform, and a maintainer of the Cutter project.
So as you can see, this research is a result of a collaboration made by Checkpoint Research Group and Intezer's research team, which was led by Itay and Omri Ben-Basad from our side. And in total, we worked on this research for a few months. So let's start. As I said, we wanted to detect connections between different Russian entities, such as a pair of malicious samples, whole families, or even between Russian actors themselves. Now, what is a connection, right? A connection can be a shared module, tool, or even a specific implementation of a function. Our research was very wide, and we weren't limited to one type of connection. Well, we had many questions in mind that we wanted to answer. For example, are the different Russian government entities working alone, or are they sharing code and techniques with each other? And if so, what artifacts, libraries, and code are more likely to be shared between two different actors, two different families? Can we support a known connection between two different families or tools, but from a technical perspective and not from the intelligence perspective? And so on and so forth. We really had many questions. And all those questions led us to start reading public information that was shared by other vendors and researchers regarding Russian attacks. There is a lot of information available out there in many reports. So that was the first step that we took. And it was a very important one. So first of all, we would like to thank all the amazing researchers who published regarding Russian attacks. It was really helpful for us. After days of reading background materials and publications, it was quite clear to us how we should proceed towards this goal of mapping the Russian ecosystem. To put it simply, we split the research into 4 steps. The first step is to collect samples that we know were attributed to Russian actors. Then we need to classify those samples, which was a very challenging step, and I'll elaborate about that. After that, we want to find the code connections, the similarities between the different samples. And lastly, analyze the interesting and relevant connections. Right, so let's start. First of all, we collected the samples. I told you we read many reports, extracted IRCs from them, and then we had to grab the actual samples, the binaries from many sources. Overall, we had approximately 2,000 unique samples to work with. The next step was to classify the samples. And although it may look easy, since the name of the attack or campaign appears in the report that we grabbed the IOCs from, classifying the samples turned out to be one of the most complicated parts of this research. And I'll explain why. First of all, there is no naming conventions for malware families and threat actors in the InfoSec industry. Every malware family and every actor have more than one name given to them by different researchers or vendors. Some vendors will use different names to describe the same family. Other malware families simply do not have a clear name. So those issues and more made us face one of the most painful drawbacks of classification and required us to be very careful when we classify a specific piece of malware to a family or an actor. But naming convention was not the only problem, and sometimes we discovered problems with the IOCs. They were too generic or even wrong. And since we needed to know exactly what every sample does, we had to dive in deeper. And we did. We built a template, 4 pieces of information that we wanted to collect for every sample of malware that we had. First of all, actor. Which actor is known or likely to have written this malware? For example, Turla, Sophacy, Gray Energy, and so on. Next, family. What is the common family name that is associated with this malware? Module. Many malware files are built in a modular way, in which the malware can extract a specific module embedded in it or download it from a C2 server. So when possible, we wanted to know whether the binary we have right now is a keylogger module, a communication module, an injection module, or anything else. And lastly, version. Some files have a clear version stamp embedded in them, and we wanted to differentiate between earlier and recent versions of the same module. At this point, we classified all our samples into 60 families and 200 different modules. So after collecting the samples and classifying them, we were ready to get to the actual thing, which is finding the code connections between the samples. And for that, we used Interzer's genetic malware analysis technology. We automatically disassembled and dissected each binary file into thousands of small fragments of assembly, also referred as genes. Then we search in which other malware samples, Russian samples, we have seen those genes in the past using this genome database made by Intezer. Now, this database contains binary genes from both previously seen malware files, but also from legitimate files. This helps us to focus only on the malicious and unique code between the samples without wasting time on shared library code, like OpenSSL, for example. Eventually, we were able to connect different samples, Russian samples, based on their pure assembly code. And every connection means that those 2 samples share code with each other that was never seen before in any other trusted software or malware which is not Russian, right? So it's really powerful. Actually, it was a bit more complex than that because some of the samples were packed in order to stay evasive, probably, so we had to automatically unpack them statically or dynamically. And the output of this process was a list with pairs of samples that share assembly code with each other. The next step was to make this list to a graph. And Itay will take it from here.
Thank you. So, as Ari said, Interzer's technology did its magic, and now we got a decent amount of data and connections to analyze. And so we searched for a way to visualize these connections and came upon this open source software called Gaffey. And Gaffey is a platform to visualize and analyze graphs. It was exactly what we were looking for. So we downloaded Gaffey, loaded our data to it, and got this as a result. Now, this is of course useless. We cannot work with it. So we had to apply some graph layout algorithms to this thing in order to make it usable. So we did, and we got much better graph with thousands of samples, thousands of nodes. Each node is a sample, of course, with a lot of clusters and a visible connections. But still, we have a problem because all we see is black nodes all over the place, and we don't have any context. What are these nodes? So we added more information. We added labels to each node with the malware family, with the name of the family of the sample, and we added colors. And each actor on the graph has its own color. So now it was much easier for us to see things in a visual way. We could simply see connections between nodes of different colors. We can see clusters of colors. It was much easier to start working. So we have this graph, and we can start looking at the connections. And we have 3 types of connections on the graph. The first one is the first type of connection is when 2 samples of the same actor and of the same malware family are sharing code with each other. And that means that these samples belong to the same malware family, basically the same different versions or different variants of the same family. The second type of connection that we have is when 2 samples of different actors are sharing code with each other. And but they are of same actor, but of different families. And this is very good for attribution. And the third type of connection that we have is, for us, the most important one, and the most interesting one is when 2 samples of different actors and of different families are sharing code with each other. So before I share with you the results of the analysis we did, let me introduce you with the first tool that we are showing today. We took this huge map from Gaffey with the thousands of nodes and turned it into what we call the Russian APT Ecosystem map. And this is a web-based map, interactive map, that you can get a better understanding of the whole ecosystem and the connections between the different families. So let's have a quick demo. Okay, so this is the map, and unlike the previous graph from Gaffey, where each node was a sample, in this map, each node represents a malware family. So we can immediately start seeing some clusters, and we can dig deeper and get the names of each family, and we can hover, for example, agent PTZ, we can hover our cursor on it and see the highlighted connection, for example, Comrade and Ruberus, and the name of the actor behind it, which is Tula. And if I click on the node, I see this sidebar on the left, which have more information about this malware family, such as the name of the family, the actor behind it, when it was first spotted in the wild, other names for the family with a short description, and references, articles, research papers that we recommend to read about this family, and of course links to integer reports down there, in which you can dig deeper inside the connections themselves, understand what pieces of assembly code are shared between samples of this family and samples of other families. So this map and the raw data that we worked in are all open source and available on our GitHub page. So make sure to try it. We invite you to do your own analysis using the map. Okay, so now that we have this huge graph from Gaffey and this map, we can start looking at the connections themselves and try to understand what are they. Are they interesting? Are they false positive? And for us as reverse engineers, this is where the fun part began. So we did. We analyzed and analyzed so many connections for days, and we really hope to find some groundbreaking findings, some new and interesting connections that nobody mentioned before. But to our disappointment, we could not find any indication that 2 different actors are sharing code with each other. We did find many examples of 2 samples of different families, but of the same actor that shared code with each other, but we could not find 2 samples of different actors that the shared connection, the shared code between them was meaningful enough to say that some module or library or functions were shared between different organizations, different Russian organizations. So at the beginning, we were quite disappointed by these results. We really hoped to find something more than that. But later we figured that the fact that no code was shared between these organizations is for itself an interesting piece of information. So we started asking ourselves why. why different organizations do not share code with each other. And while we could come up with some theories, the truth is that we really don't know. And we have no one to ask, and if we did, I'm not sure it will be wise. But we have some theories, and maybe the first one, maybe the strongest one is that Russia is well aware for the importance of a good OPSEC. And let's have a quick pros and cons for the decision not to share code in terms of OPSEC. Russia knows that if two different organizations will share code with each other, in case where two different operations will share code with each other, in case where one operation will get caught by security researchers, by security vendors, it will put the other operations at risk. So making sure the code is entirely separated will make sure that this is not going to happen. Because nowadays we use code attribution and consistency as a very good way to detect new operations. But it comes with a cost, and an expensive one. Because if this theory is true, that means that Russia is willing to invest a lot of money, a lot of time, a lot of man-hours in having different teams of malware developers writing the exact same functionality over and over again, instead of reusing the existing knowledge, existing modules. And this is very expensive. The second theory that we have is that Russia is that the different organizations do not share code due to internal politics. And while this might be the case, we are not too familiar with the internal relationships between the different organizations under the Russian government, so we just wanted to point it out as a possible option, but we don't have a lot of information to support it. So we did not find the cross-actor connections we wanted to, but we do have a lot of data to work with. We did enormous analysis of so many samples, and we can still use this data. And you already saw it in the APT map that we shared. But we also wrote another tool, and even more practical this time. So having access to thousands of samples and millions of pieces of code that were shared between these samples allowed us to understand which pieces of code, which genes are more likely to be shared between the Russian organizations. So we took each family and took all these samples of this family and found the unique genes of samples of this family that were repeated over and over again, that were so popular. So we automatically generated Yara signatures for them. And we took all these Yara signatures for all these families, put them in a Yara rule set, wrapped it up together in a Python script and executable. And we are sharing with you this tool that you can scan your system, your files, against known and unknown Russian MPTs. And of course, this tool and the rule set and the Yara rules are all open source and available on GitHub, so you can simply take it and put it in your favorite Yara scanners and your favorite systems. And we invite you to give it a try, give us your feedback about this tool, even contribute to the project. Just a few weeks ago, we got a very nice contribution from an external user that made this tool cross-platform, so now it can run on Windows, Linux, and Mac. So please don't hesitate to try it. And that's it. Thank you very much for listening.